The 45-degree angle is a fundamental concept in geometry, physics, and design, often appearing in practical and theoretical contexts. Two application examples in which the right angle and the Thales theorem are included refer to animations. In physics, a 45-degree trajectory maximizes the distance a projectile can travel, a principle rooted in the balance between vertical and horizontal motion. Architects use 45-degree angles in structures like doors and window grills, blending functionality with aesthetic appeal. To construct a 45-degree angle, one might first create a 90-degree angle and then bisect it, a method achievable with tools like a compass and protractor. These examples highlight the angle's versatility, from mathematical precision to real-world applications. For instance, in digital interfaces, a 45-degree angle is often used in the layout of icons or the tilt of screens to optimize ergonomics and visual appeal. This angle allows for a balance between usability and aesthetic harmony, reducing eye strain while maintaining a dynamic feel. In photography, photographers sometimes adjust their camera angles to 45 degrees to capture more of the scene's depth, creating a sense of spatial awareness in their compositions. Another intriguing application lies in the field of robotics, where 45-degree joints are common in articulated limbs. This angle provides a range of motion that is both efficient and stable, enabling robots to navigate complex environments. Additionally, in the world of sports, athletes like gymnasts and divers often use 45-degree angles in their routines to maximize lift and control, demonstrating the angle's role in human performance. Even in everyday objects, such as the design of staircases or the slope of ramps, a 45-degree angle is frequently employed to balance accessibility and structural integrity. This angle allows for a gentle incline that is easier to navigate while minimizing the risk of instability. These examples underscore how the 45-degree angle, though simple in measure, is a versatile and essential element in both natural and human-made systems. The 45-degree angle holds a unique place in both practical applications and theoretical understanding. For each sentence, assess whether it should remain unchanged or require adjustment based on evidence. This principle, rooted in the balance between vertical and horizontal velocity components, is a cornerstone of classical mechanics and will be explored in depth during your studies. In architecture, the 45-degree angle is often employed to create aesthetically pleasing designs, such as the diagonal lines in window grills or the symmetry of certain door structures. This angle's geometric properties make it versatile for both functional and decorative purposes. Mathematically, a 45-degree angle is half of a right angle, and it plays a key role in trigonometry. For instance, dividing a 180-degree straight line into 4 equal parts results in 4 45-degree angles, demonstrating its role in geometric division. When measuring such angles, a protractor is essential, aligning the tool's baseline with one arm of the angle and checking the other against the 45-degree mark. The complement of a 45-degree angle is also 45 degrees, as two such angles sum to 90 degrees. Halving a 45-degree angle yields a 22.5-degree angle, achievable through an angle bisector. These properties underscore the angle's significance in both basic and advanced mathematical contexts. While the examples provided illustrate its utility, it's important to note that such concepts are often contextualized within broader scientific and historical frameworks. For instance, the study of angles in geometry has evolved over centuries, influenced by ancient civilizations like the Greeks and later formalized through modern mathematical rigor. However, the specific details here are grounded in the examples and explanations shared, ensuring clarity without overreaching into unverified claims. The program's structure emphasizes interdisciplinary engagement, blending historical analysis with contemporary political theory and technological innovation. For instance, the Digital Transformations Beyond the West module challenges students to assess how non-Western nations navigate digital sovereignty, contrasting with Western-centric narratives of tech dominance. Similarly, the Cybersecurity Governance module interrogates the ethical and strategic dilemmas of state surveillance, data breaches, and the role of international law in mitigating cyber threats. These modules collectively prepare students to critically evaluate the interplay between power, technology, and global governance, fostering analytical frameworks applicable to real-world conflicts, policymaking, and cultural shifts. By integrating historical context with modern case studies, the curriculum aims to cultivate scholars and practitioners capable of addressing the complexities of an interconnected yet fragmented global order. A 45-degree angle is a fundamental concept in geometry, often encountered in both theoretical and practical contexts. Thales' theorem states that an angle inscribed in a semicircle is a right angle. In architecture, this angle is frequently used to design aesthetically pleasing structures, such as the intricate patterns in doors and window grills. Consider the example of dividing a straight line into equal parts. If a 180-degree straight line is split into 4 equal segments, each segment measures 45 degrees. This division illustrates how angles can be systematically broken down, a principle that underpins many geometric constructions. Another example involves the complement of a 45-degree angle, which is also 45 degrees, as the sum of complementary angles must equal 90 degrees. This symmetry highlights the angle's role in right-angle geometry. When measuring a 45-degree angle, a protractor is the standard tool. By aligning the protractor's baseline with one arm of the angle and the vertex at the center, the second arm should intersect the 45-degree mark. This method ensures precision in both educational settings and real-world applications. The versatility of a 45-degree angle extends beyond mathematics. In history, such angles might appear in architectural remnants or artifacts, offering clues about the techniques and aesthetics of past civilizations. However, interpreting these details requires careful analysis, as seen in historical evidence sheets that guide students to distinguish between observable facts and inferred conclusions. While the 45-degree angle itself is a mathematical certainty, its cultural or historical significance often depends on context, which must be approached with methodological rigor. Ultimately, the 45-degree angle remains a cornerstone of geometric understanding, bridging abstract theory with tangible applications. Its study not only enhances technical skills, but also fosters critical thinking, whether in a classroom or when examining historical artifacts. The interplay between historical analysis and contemporary policymaking becomes evident when examining how the skills honed in source criticism exercises, such as discerning material culture or contextualizing visual cues, mirror the methodologies required to interpret geopolitical texts or archival records. For instance, the meticulous observation of a scene's physical details, as practiced in the evidence sheet, parallels the rigorous scrutiny of primary sources in international relations, where distinguishing between propaganda and factual documentation is critical. This connection underscores the universal value of critical thinking across disciplines, whether assessing a 19th-century treaty draft or evaluating the authenticity of a historical artifact. Such interdisciplinary approaches often reveal how seemingly disparate fields share foundational techniques, reinforcing the idea that education transcends siloed knowledge. The 45-degree angle, a unique geometric measurement, appears in various practical and theoretical contexts. In architecture, it is often used to design aesthetically pleasing structures, such as doors and window grills, where symmetry and balance are key. Similarly, in physics, a 45-degree angle is optimal for maximizing the distance a projectile, like a ball, can travel when thrown. This principle is rooted in the balance between vertical and horizontal components of motion, which is why it's a common topic in physics education. Solar panels are also often angled at 45 degrees to optimize sunlight absorption, depending on geographical location and seasonal variations. These examples highlight the angle's utility in both natural and engineered systems. The 45-degree angle is also mathematically significant. It is half of a right angle, 90 degrees, and forms a complementary pair with itself, as 45 plus 45 equals 90. This property makes it a key element in geometry, particularly in isosceles right triangles, where the two non-right angles are each 45 degrees. When bisecting a 90-degree angle, the resulting angles are 45 degrees, a method often used in construction and design. Additionally, a full rotation of 360 degrees contains 8 45-degree angles, illustrating its role in circular measurements. Educational examples further clarify its applications. For instance, dividing a straight line 180 degrees into 4 equal parts results in 4 45-degree angles, demonstrating how angles can be subdivided systematically. Another example involves calculating the complement of a 45-degree angle, which is also 45 degrees, as the sum of complementary angles must equal 90 degrees. These exercises reinforce the angle's mathematical properties and its relevance in problem solving. While the 45-degree angle is well documented in geometry and applied sciences, its historical and cultural significance is less emphasized. However, its presence in everyday objects and natural phenomena underscores its practical importance. The angle's simplicity and versatility make it a foundational concept in both theoretical and real-world contexts, bridging mathematics, physics, and design. By understanding its properties and applications, students can appreciate its role in shaping the world around them. The evidence sheet is a core tool in history education, designed to sharpen students' critical thinking by connecting observable details to historical reasoning. An angle bisector of a 90-degree angle creates two angles, each measuring 45 degrees. This left column serves as the foundation for their analysis, ensuring they base their conclusions on concrete observations rather than assumptions. On the right, they write what each detail proves or rules out, building logical connections between the visible and the historical. The year is guessed last, emphasizing the importance of reasoning over mere guesswork. In practice, teachers model the first round on a projector, guiding students to record 5 solid observations before moving to the next phase. The year slider remains untouched until the right-hand column is complete, reinforcing the necessity of thorough analysis. After the game, students reflect on which single detail most influenced their estimate, considering whether that detail could have been restored, rebuilt, or faked. They also identify what elements were absent from the scene that would be necessary for a confident date. Finally, they evaluate their own and others' reasoning, recognizing that the gap between a confident inference and a weak one defines the mark scheme. This process cultivates historical literacy by prioritizing evidence, logic, and critical engagement over speculation. The evidence sheets, with their emphasis on source criticism and contextual reasoning, underscore the importance of critical thinking in historical analysis. By requiring students to distinguish between observable facts and inferred conclusions, these tools foster a deeper engagement with primary sources. This skill is not confined to history. It mirrors the analytical rigor needed in fields like science, where data interpretation is paramount. For instance, just as historians must scrutinize artifacts to discern their cultural significance, engineers analyzing structural angles must verify measurements against theoretical models. Both disciplines rely on systematic observation and logical deduction to bridge gaps between evidence and understanding. The interplay between these methodologies highlights how education cultivates versatile critical thinking, applicable across diverse domains. The program's interdisciplinary approach ensures students engage with contemporary challenges, such as the ethical implications of data science in foreign policy or the role of digital sovereignty in global governance. By integrating historical analysis with modern technological shifts, graduates are equipped to navigate complex issues like misinformation campaigns, algorithmic bias, and the geopolitical competition over digital infrastructure. This blend of theory and practice prepares them for careers in diplomacy, policy analysis, or tech-driven governance, where understanding both past conflicts and emerging threats is critical. The curriculum also emphasizes critical thinking, encouraging students to question assumptions about power dynamics and the evolving nature of statehood in an interconnected world. The 45-degree angle, a critical geometric measure, appears in numerous practical and theoretical contexts. In physics, it is optimal for maximizing the distance of projectile motion, such as when throwing a ball or positioning solar panels to capture sunlight efficiently. Architecturally, it is used in designs for doors, windows, and decorative elements, offering both aesthetic appeal and structural balance. Mathematically, a 45-degree angle is half of a right angle, making it a key component in calculations involving complementary angles, where two 45-degree angles sum to 90 degrees. Its bisector creates a 22.5-degree angle, demonstrating its role in subdividing angles for precision. These applications highlight its versatility across disciplines. The 45-degree angle's significance extends to historical and academic contexts. For instance, in educational frameworks, it is often used as a foundational concept in geometry, serving as a bridge between basic angles and more complex trigonometric principles. Its study is integral to fields like engineering, where precise angle measurements are essential for construction and design. Additionally, the angle's properties are explored in historical analysis, such as in the study of ancient architectural techniques or the evolution of mathematical thought. These connections underscore its enduring relevance. In the realm of historical inquiry, tools like the evidence sheet help students critically analyze sources. By listing observable details, such as materials, tools, or signage, and linking them to inferred historical contexts, students develop skills in source criticism. For example, a scene depicting a 45-degree angle in a historical artifact might prompt questions about its functional purpose or symbolic meaning. Similarly, academic programs in international relations and history often integrate interdisciplinary approaches, examining how historical events shape contemporary political and economic systems. These frameworks emphasize the importance of contextual analysis, much like the logical reasoning required to understand geometric principles. While the 45-degree angle itself is a mathematical concept, its applications and interpretations span diverse fields. From practical engineering to historical analysis, it serves as a bridge between abstract theory and real-world application. By examining its role in both technical and academic domains, we gain a deeper appreciation for its significance in shaping human understanding and innovation. The 45-degree angle is a fundamental concept in geometry, physics, and design. The rule of 3-4-5 is derived from the Pythagorean triple, 3, 4, 5, and is used by carpenters and masons to confirm right angles. This principle is foundational in understanding motion and will be explored in greater depth in advanced studies. In architecture, 45-degree angles are used to create aesthetically pleasing structures, such as the diagonal lines in doors and window grills, which add both functionality and visual appeal. Mathematically, a 45-degree angle is half of a 90-degree right angle, making it a key component in isosceles right triangles. For instance, 1/4 of a 180-degree straight angle results in a 45-degree angle, demonstrating its role in dividing angles proportionally. When a straight line is divided into 4 equal parts, each segment measures 45 degrees, illustrating its symmetry. The complement of a 45-degree angle is also 45 degrees, as the sum of complementary angles must equal 90 degrees. Halving a 45-degree angle produces a 22.5-degree angle, which can be constructed using an angle bisector. To draw a 45-degree angle, one typically starts by constructing a 90-degree angle and then bisecting it. In practical terms, 8 45-degree angles make a full 360-degree rotation, highlighting its relevance in navigation and design. Measuring a 45-degree angle requires a protractor, aligning the tool's baseline with one arm of the angle and checking if the other arm matches the 45-degree mark. These examples underscore the versatility of the 45-degree angle across disciplines, from theoretical mathematics to real-world applications. In addition to its role in architecture and physics, a 45-degree angle also appears in everyday technology, such as in the design of laptop screens and smartphone cameras. The diagonal angle of a 45-degree tilt allows for optimal viewing angles and balance between portability and functionality. In sports, athletes often use 45-degree angles for maximum reach, such as in basketball when shooting from the corners of the court, or in golf when positioning for a drive. Even in nature, 45-degree angles can be observed in the way light refracts through water droplets, creating rainbows, or in the slope of hills that naturally form such angles due to erosion. These instances highlight how the 45-degree angle, though simple in measure, underpins complex interactions in both man-made and natural systems. The 45-degree angle is a fundamental concept in geometry, often encountered in both theoretical and practical contexts. Its significance lies in its balance between acute and right angles, making it versatile for various applications. For instance, when a straight line, 180 degrees, is divided into 4 equal parts, each segment measures 45 degrees. This is achieved by first splitting the straight line into two 90-degree angles and then bisecting each 90-degree angle into two 45-degree angles, resulting in 4 equal 45-degree angles in total. In physics, a 45-degree angle is optimal for projectile motion, as it maximizes the horizontal distance traveled when neglecting air resistance. This principle is foundational in kinematics. In architecture, 45-degree angles are used in designing elements like window grilles and doors, where symmetry and structural stability are key. Mathematically, the complement of a 45-degree angle is another 45-degree angle, since complementary angles sum to 90 degrees. Halving a 45-degree angle yields a 22.5-degree angle, which can be constructed by bisecting the 45-degree angle using a compass and straightedge. To draw a 45-degree angle, one typically constructs a 90-degree angle first and then bisects it. The 45-degree angle's simplicity and utility make it a recurring theme in mathematics, engineering, and design, underscoring its importance in both academic and real-world scenarios. The Cybersecurity Governance module also explores the role of international coalitions, such as the Budapest Convention on Cybercrime, and debates over sovereignty versus global cooperation in addressing cyber threats. Students analyze how state and non-state actors navigate legal, ethical, and technical challenges, such as ransomware attacks, disinformation campaigns, and the militarization of cyberspace. The module emphasizes interdisciplinary approaches, combining legal frameworks, technological analysis, and geopolitical strategy to evaluate responses to emerging risks. By linking historical precedents in global governance, such as the creation of the United Nations, to contemporary digital challenges, students develop a nuanced understanding of how institutions adapt to protect national interests while fostering international collaboration. Students in the Cybersecurity Governance module examine emerging threats such as state-sponsored cyber attacks and data breaches, analyzing how international frameworks attempt to address these challenges. They also explore the limitations of current governance structures and debate potential reforms to enhance global cooperation and resilience against cyber threats. This includes evaluating the role of public-private partnerships, the ethical implications of surveillance technologies, and the balance between national security and digital privacy. By engaging with case studies from recent geopolitical conflicts and technological advancements, students develop critical perspectives on the evolving landscape of cybersecurity policy and its impact on global stability. A 45-degree angle is a fundamental concept in geometry, often encountered in various real-world applications and mathematical problems. Here's a concise overview of its significance, examples, and related questions. Key concepts. A 45-degree angle is an acute angle formed when two lines intersect, creating a measure of exactly 45 degrees. It is half of a right angle, 90 degrees, and is unique in its balance between steepness and flatness, making it versatile in practical scenarios. Applications and examples. 1. Physics and projectile motion. When throwing a ball, a 45-degree angle maximizes horizontal distance due to the optimal balance between vertical and horizontal velocity components. This principle is foundational in kinematics. Example 1. If a ball is thrown with a 45-degree angle, its trajectory will cover the farthest distance compared to other angles, assuming no air resistance. 2. Architecture and design. 45-degree angles are used in constructing symmetrical designs, such as window grills, door frames, and decorative elements. They add aesthetic appeal while maintaining structural integrity. Example 2. A straight line divided into 4 equal parts creates 4 45-degree angles, commonly seen in grid layouts or geometric patterns. 3. Mathematical problems mask the complementary angles. A 45-degree angle's complement is also 45 degree, as 90 degrees minus 45 degrees equals 45 degrees. Bisecting angles. Half of a 45-degree angle is 22.5 degrees, achieved by bisecting it with an angle bisector. FAQs. What does a 45-degree angle look like? It resembles the open jaw of scissors or the angle formed by the diagonal of a square. It is less steep than a 90-degree angle, but more than a 30-degree angle. How to measure a 45-degree angle? Use a protractor, align the vertex with the protractor's center, and check if the arm aligns with the 45-degree mark. How many 45-degree angles make a full turn? A full circle, 360 degrees, contains 8 45-degree angles. 360 divided by 45 equals 8. Why is 45 degrees optimal for projectile motion? At 45 degrees, the vertical and horizontal components of velocity are equal, maximizing the range under gravity. Conclusion. The 45-degree angle is a cornerstone of geometry, blending practical utility with theoretical elegance. Its applications span physics, architecture, and mathematics, underscoring its relevance in both academic and real-world contexts. Understanding its properties and uses enhances problem-solving skills across disciplines. The 45-degree angle is a fundamental concept in geometry, physics, and design, characterized by its unique properties and applications. Here's a concise overview of its significance and examples. 1. Physics and motion. A 45-degree angle is optimal for projectile motion as it balances vertical and horizontal velocity components, maximizing distance traveled. This principle is foundational in physics and engineering. 2. Geometry and construction. Angle bisector. A 45-degree angle is formed by bisecting a 90-degree right angle, making it a key component in creating symmetrical designs. Architecture. Used in designing doors, window grills, and structural elements for aesthetic and functional balance. 3 mathematical examples. Mach minus example 1. 1/4 of a 180-degree straight angle is 45 degrees. Mach minus example 2, dividing a straight line 180 degrees into 4 equal parts results in 4 45-degree angles. 4 complementary and halved angles. The complement of a 45-degree angle is 45 degrees, since 90 degrees minus 45 degrees equals 45 degrees. Half of a 45-degree angle is 22.5 degrees, achieved by bisecting it further. 5. Measurement and drawing. A protractor is used to measure a 45-degree angle by aligning its baseline with one arm of the angle and checking the other arm against the 45-degree mark. Constructing a 45-degree angle involves first creating a 90-degree angle and then bisecting it. 6. Real-world applications. The scissors and tools. The open face of scissors resembles a 45-degree angle. Navigation and design, used in creating diagonals in art, engineering, and urban planning. While the provided evidence sheets and academic modules relate to history and international relations, they appear unrelated to the geometric focus of the 45-degree angle. The examples and explanations here emphasize its mathematical and practical relevance, avoiding speculative or unsupported claims. The program's interdisciplinary approach ensures students engage with contemporary global challenges, from climate policy to digital sovereignty, while fostering analytical rigor. Graduates often pursue careers in think tanks, governmental agencies, or international organizations, leveraging skills in critical theory, data analysis, and historical contextualization. For those interested in further specialization, the program's flexibility allows for interdisciplinary minors in areas like environmental policy or media studies, though such pathways require careful coordination with academic advisors. The curriculum's emphasis on digital tools and global interconnectedness also positions students to navigate the complexities of modern diplomacy, where traditional boundaries between state and non-state actors blur. This blend of theoretical depth and practical relevance underscores the program's role in shaping informed, adaptable leaders for an increasingly interdependent world. For instance, solar panels are often angled at 45 degrees to maximize sunlight absorption, depending on geographical location. Similarly, when throwing a ball, a 45-degree trajectory optimizes distance, a principle explored in physics. In architecture, 45-degree angles are used in designs for doors, windows, and decorative elements, adding both functionality and aesthetic appeal. These angles also appear in everyday objects, such as the blades of scissors or the open face of a pair of scissors, which resemble the shape of a 45-degree angle. Mathematically, a 45-degree angle is half of a 90-degree right angle, making it a key component in geometry. For example, dividing a straight line, 180 degrees, into 4 equal parts results in 4 45-degree angles. This concept is useful in construction and design, where precise measurements are critical. Additionally, a 45-degree angle is complementary to another 45-degree angle, as their sum equals 90 degrees. If a 45-degree angle is bisected, it creates two 22.5-degree angles, demonstrating how smaller angles can be derived from larger ones. The 45-degree angle also has historical and cultural significance. In ancient architecture, such angles were used to create symmetrical structures, reflecting a blend of mathematical precision and artistic expression. Modern applications extend to technology, such as in the design of computer screens, or the angles used in digital interfaces to enhance user experience. These examples highlight the versatility of 45-degree angles across disciplines. When measuring a 45-degree angle, a protractor is typically used. The base of the angle is aligned with the protractor's straight edge, and the vertex is placed at the center. The second arm of the angle is then checked against the 45-degree mark. This method ensures accuracy in fields ranging from engineering to art. The 45-degree angle's simplicity and utility make it a foundational concept in both theoretical and applied contexts. Its presence in nature, technology, and human-made structures underscores its relevance. Whether in the design of a building or the calculation of a projectile's path, the 45-degree angle remains a cornerstone of geometric understanding. A 45-degree angle is a fundamental concept in geometry, often encountered in various real-world applications. In physics, it is noted that a 45-degree angle is optimal for projectile motion, as it maximizes the horizontal distance a ball can travel when thrown. This principle is explored in depth in later studies. In architecture, 45-degree angles are used to design elements like doors and window grills, adding both aesthetic and structural value. Mathematically, a 45-degree angle is half of a right angle, and its complement is also 45 degrees, since the sum of complementary angles is 90 degrees. To construct a 45-degree angle, one can bisect a 90-degree angle using a compass. For instance, dividing a straight line 180 degrees into 4 equal parts results in 4 45-degree angles. Additionally, 8 45-degree angles make a full rotation of 360 degrees. These examples illustrate the versatility and significance of the 45-degree angle across disciplines. The program's interdisciplinary approach ensures students engage with contemporary issues through both theoretical and practical lenses. For instance, the Digital Transformations Beyond the West module's exploration of state and corporate influence in Asia directly ties to modern debates about digital sovereignty and tech monopolies. Similarly, the Cybersecurity Governance module's analysis of global governance frameworks, such as the Budapest Convention on Cybercrime, prepares students to navigate the complexities of international law in an era of cyber threats. These modules collectively equip students with the analytical tools to address challenges like misinformation, geopolitical tensions, and the ethical implications of AI, bridging academic rigor with real-world relevance. The interdisciplinary nature of critical thinking skills cultivated in programs like international relations and political history also finds resonance in fields such as architecture, engineering, and design, where precise angular measurements like 45 degrees underpin structural integrity and aesthetic balance. For instance, the principles of angle bisecting or spatial reasoning taught in geometry courses mirror the analytical frameworks used in assessing historical sources or interpreting global political dynamics. Both domains require discerning patterns, evaluating evidence, and synthesizing complex information to arrive at informed conclusions. This interconnectedness underscores how foundational skills in one discipline can inform and enhance understanding in another, fostering a holistic approach to problem-solving across disciplines. A 45-degree angle is a common geometric measurement with practical applications in various fields. For instance, solar panels are often angled at 45 degrees to optimize sunlight absorption, particularly in regions with specific geographical conditions. Similarly, in physics, a 45-degree trajectory is ideal for maximizing the distance a projectile, like a thrown ball, can travel. This principle is foundational in kinematics, where angles of projection directly influence range. In architecture, 45-degree angles are used in design elements such as doors and window grills, adding both aesthetic and structural value. The complement of a 45-degree angle is another 45 degrees, as two such angles sum to 90 degrees. Halving a 45-degree angle results in a 22.5-degree angle, which can be constructed using an angle bisector. Measuring a 45-degree angle requires a protractor, aligning the baseline with the angle's vertex, and checking the other arm against the 45-degree mark. A full rotation of 360 degrees contains 8 45-degree angles, highlighting its role in circular measurements. Beyond geometry, 45-degree angles appear in everyday scenarios. For example, dividing a straight line into 4 equal parts creates 4 45-degree angles, demonstrating how basic geometric principles underpin practical problem solving. These examples underscore the versatility of 45-degree angles in both theoretical and applied contexts. In educational settings, students explore such concepts through activities like the evidence sheet, where they analyze historical scenes by listing observable details and inferring their implications. This method fosters critical thinking by linking physical observations to broader historical contexts. Similarly, Academic programs in international relations integrate interdisciplinary modules, such as the study of globalization's historical roots or cybersecurity governance, to develop nuanced understanding of complex global issues. These approaches emphasize the importance of evidence-based reasoning and interdisciplinary analysis in both scientific and historical inquiry. By connecting geometric principles to real-world applications and historical analysis, such topics illustrate how foundational concepts shape diverse fields, from engineering to social sciences. This interplay between theory and practice highlights the enduring relevance of 45-degree angles and similar principles in advancing knowledge and solving practical challenges. Important geometrical concepts include perpendicular lines, which form right angles at their intersection, and orthogonality, a property of forming right angles typically applied to vectors. The presence of a right angle in a triangle is a defining characteristic of right triangles, which are fundamental to trigonometry. The term right in right angle may derive from the Latin rectus, straight, and the Greek orthos, upright, both related to perpendicularity. For instance, in the International Relations and Politics program at Constructor University, students explore such interdisciplinary connections, examining how theoretical frameworks in political science intersect with practical applications in global governance and data science. In architecture, the 45-degree angle is a design staple, enabling the creation of aesthetically pleasing and structurally sound elements like doorways and window grills. This geometric precision reflects a broader trend in design, where mathematical principles inform both functionality and beauty. Meanwhile, historical analysis, as seen in the History of Globalization module, reveals how such angles, both literal and metaphorical, shape human interactions. For example, the digital transformations discussed in the program mirror the interconnectedness of societies, much like the geometric interplay of angles in a 45-degree example. When students engage with these concepts, they develop critical thinking skills, learning to dissect complex systems, whether in physics, politics, or history. The 45-degree angle thus becomes a symbol of the interplay between theory and application, a theme echoed in academic disciplines worldwide. By examining such angles, students not only grasp mathematical principles, but also appreciate their role in shaping the world around them. The history worksheet's emphasis on observable details and critical reasoning mirrors the analytical rigor required in the IRPH program's modules. A scene depicting a 19th-century printing press, for example, could spark discussions about the role of information control in shaping modern cybersecurity governance, a theme central to the cybersecurity governance module. By training students to distinguish between what is visible and what is inferred, the worksheet cultivates the skepticism and precision needed to dissect complex historical and political phenomena. This interplay between tangible evidence and abstract theory becomes a cornerstone of their academic development, bridging the gap between classroom analysis and real-world policymaking. In engineering, solar panels are often angled at 45 degrees to optimize sunlight absorption, aligning with geographical latitude for maximum efficiency. Similarly, in physics, projectile motion demonstrates that a 45-degree launch angle achieves the farthest horizontal distance, a principle rooted in the balance of vertical and horizontal velocity components. Two application examples in which the right angle and Thales' theorem are included. Beyond these applications, the 45-degree angle holds mathematical significance. It is half of a right angle, making it a key component in geometry and trigonometry. For instance, dividing a 90-degree angle into two equal parts yields two 45-degree angles, a concept used in constructing angle bisectors. The complement of a 45-degree angle is also 45 degrees, as complementary angles sum to 90 degrees. Additionally, a 45-degree angle is half of a 90-degree angle, which can be further bisected to create 22.5-degree angles. These relationships highlight the angle's role in foundational geometric principles. Practical methods for constructing a 45-degree angle include using a protractor or compass. By first creating a 90-degree angle and then bisecting it, one can achieve the desired measurement. This technique is essential in fields requiring precise angular measurements, such as drafting or construction. Furthermore, a full rotation of 360 degrees contains 8 45-degree angles, illustrating the angle's divisibility and utility in circular measurements. While these examples underscore the 45-degree angle's versatility, its relevance extends beyond mathematics. In historical analysis, tools like the evidence sheet from HistoryGuesser.app encourage students to interpret visual details to infer contextual information, a skill that parallels the logical reasoning required to understand geometric principles. Similarly, academic programs in international relations, such as those at Constructor University, emphasize critical thinking and interdisciplinary analysis, skills that align with the analytical approach needed to grasp the significance of angles in both theoretical and applied contexts. These connections demonstrate how mathematical concepts like the 45-degree angle intersect with broader intellectual disciplines, reinforcing their importance in shaping understanding across fields. The evidence sheet for historical analysis encourages students to critically engage with visual sources by distinguishing between observable details and inferred conclusions. By listing physical elements like materials, tools, or signage in the left column, students practice grounding their interpretations in tangible evidence. The right column then explores what these observations imply or exclude, fostering analytical reasoning. This method emphasizes the importance of avoiding assumptions, such as mistaking a modern object for an ancient one, and instead focusing on the logic of deductions. The final step, guessing the year, requires synthesizing all observations, with the justification rooted in the reasoning process rather than the accuracy of the guess itself. This approach cultivates historical thinking by prioritizing evidence-based arguments over speculative conclusions. In parallel, academic programs in international relations and politics, such as those at Constructor University, integrate rigorous theoretical and practical training. Students explore the interplay between economics and global politics, examining how shifts in power dynamics, like China's rise, reshape international systems. Modules on advanced theory challenge students to debate foundational concepts in world politics, while courses on globalization's history trace the interconnectedness of societies across centuries. Electives like Digital Transformations Beyond the West analyze how non-Western regions navigate technological change, and Cybersecurity Governance addresses modern threats to global stability. These disciplines mirror the evidence sheet's emphasis on critical analysis, as students must dissect complex systems, whether historical or geopolitical, to uncover underlying patterns and tensions. Both the history worksheet and academic modules underscore the value of structured inquiry. The evidence sheet trains students to question assumptions and refine their reasoning, while university programs equip them to apply analytical frameworks to real-world challenges. Together, they illustrate how critical thinking, rooted in observation, logic, and evidence, remains central to understanding both past and present complexities. By balancing meticulous observation with intellectual rigor, these methods prepare learners to navigate ambiguity and construct persuasive, well-supported arguments. The 45-degree angle is a fundamental concept in geometry, often encountered in real-world applications and mathematical problems. For instance, when dividing a straight line 180 degrees into 4 equal parts, each segment measures 45 degrees, as demonstrated in example 1. Similarly, splitting a right angle 90 degrees into 2 equal parts creates two 45-degree angles, as seen in example 2. These angles are also pivotal in fields like architecture, where they are used to design symmetrical structures, and in physics, where they optimize projectile motion. The evidence sheets provided, however, shift focus to historical analysis and academic programs. The first sheet encourages critical thinking by linking observable details in a scene to inferred historical contexts, while the second outlines a university program in international relations. These are distinct from mathematical concepts but reflect broader educational frameworks. When engaging with such materials, it is essential to rely on verifiable observations and avoid speculative interpretations, as emphasized in the source rules. In summary, the 45-degree angle remains a practical tool in mathematics and design, while the historical evidence sheets serve as resources for contextual analysis in education. Both domains require careful, evidence-based reasoning to ensure accuracy. The interdisciplinary approach of the program ensures students engage with both theoretical frameworks and practical applications, preparing them for careers in diplomacy, policy analysis, or global governance. For instance, the integration of data science in modules like foreign policy, diplomacy, and data science equips students to analyze large datasets, predict geopolitical trends, and assess the effectiveness of international agreements. Similarly, the Digital Transformations Beyond the West module encourages critical examination of how non-Western nations navigate technological sovereignty, challenging Eurocentric narratives in global digital policy. This blend of historical context, theoretical rigor, and technical skills fosters a nuanced understanding of contemporary challenges, such as climate diplomacy or digital authoritarianism, while emphasizing the importance of cultural and geopolitical diversity in shaping international relations. The modules within the International Relations and Politics program emphasize interdisciplinary approaches, often intersecting with fields like technology, economics, and cultural studies. For instance, the Digital Transformations Beyond the West module examines how non-Western societies navigate digital shifts, a topic that could intersect with architectural design principles, such as the use of 45-degree angles in sustainable infrastructure. Similarly, the Cybersecurity Governance module might explore how geometric principles, including angles, are applied in network layouts or data encryption algorithms. These connections highlight how academic disciplines often rely on foundational concepts from diverse areas, even if the direct link isn't always explicit. Students are encouraged to recognize such overlaps, fostering a holistic understanding of complex global issues. Important geometrical concepts include perpendicular lines, which form right angles at their intersection, and orthogonality, a property of forming right angles typically applied to vectors. In physics, it is the optimal angle for maximizing the distance a projectile travels, as it balances vertical and horizontal velocity components. This principle is foundational in kinematics and is often introduced in early physics education. In architecture, 45-degree angles are used to design aesthetically pleasing structures, such as the diagonal elements in modernist buildings, or the intricate patterns in window grills. Mathematically, a 45-degree angle is a key component of isosceles right triangles, where the two non-right angles are equal and its complement is also 45 degrees, making it a critical concept in trigonometry. Practical examples further illustrate its utility. For instance, dividing a straight line 180 degrees into 4 equal parts results in 4 45-degree angles, demonstrating how geometric principles underpin spatial reasoning. When measuring a 45-degree angle, a protractor is used by aligning the vertex with the tool center and checking if the second arm matches the 45-degree mark. Additionally, bisecting a 90-degree angle yields two 45-degree angles, a technique often taught in geometry classes. These applications highlight the angle's role in both theoretical understanding and real-world problem-solving. The Cybersecurity Governance module considers which threats to cybersecurity have emerged, analyzes the global governance efforts that have been made to tackle these threats, and reflects on how these efforts could be organized differently. Students engage with case studies of cyber attacks, data breaches, and state-sponsored hacking campaigns to understand the evolving landscape of digital security. They also explore the role of international organizations such as the United Nations and the International Telecommunication Union in shaping norms and frameworks for cyber defense. The module emphasizes the tension between national sovereignty and global cooperation, asking whether decentralized approaches or centralized governance structures are more effective in addressing transnational cyber risks. By the end of the course, students are expected to critically assess the ethical, legal, and strategic dimensions of cybersecurity policy in an interconnected world. The Cybersecurity Governance module also explores case studies of cyber conflicts, such as state-sponsored hacking incidents and data breaches, to analyze how nations and international bodies respond to digital threats. Students critically assess the effectiveness of treaties like the Budapest Convention on Cybercrime and debate the ethical implications of surveillance technologies in balancing security and privacy. This module often intersects with the digital transformations beyond the West course, where students examine how non-Western states navigate global tech power dynamics, such as China's influence over data infrastructure or India's regulatory approaches to digital sovereignty. Such interdisciplinary connections highlight the program's emphasis on contextualizing theoretical frameworks within real-world geopolitical and historical contexts, preparing students to address complex challenges in an interconnected world. The 45-degree angle is a fundamental concept in geometry, physics, and design. For each sentence, decide whether it should remain unchanged or require adjustment. For instance, 1/4 of a 180-degree straight angle equals 45 degrees, and dividing a 90-degree angle into two equal parts creates two 45-degree angles. This angle is often used in practical applications, such as throwing a ball for maximum distance, where a 45-degree trajectory optimizes horizontal and vertical motion. In architecture, 45-degree angles are employed in creating symmetrical designs for doors, windows, and decorative elements. When measuring a 45-degree angle, a protractor is used by aligning the vertex with the tool's center and checking if the other arm matches the 45-degree mark. To construct a 45-degree angle, one can bisect a 90-degree angle using a compass. The complement of a 45-degree angle is also 45 degrees, as 90 degrees minus 45 degrees equals 45 degrees, and half of a 45-degree angle is 22.5 degrees, achieved by bisecting it further. The 45-degree angle's significance extends beyond mathematics, influencing fields like engineering, art, and history. For example, historical reconstructions or educational tools might use 45-degree angles to model architectural elements or analyze spatial relationships. However, such applications require careful contextual analysis, as demonstrated in historical evidence sheets, which emphasize verifying observable details before drawing conclusions. While the 45-degree angle's mathematical properties are well defined, its real-world interpretations depend on precise measurements and contextual validation. The Cybersecurity Governance module also explores the ethical dilemmas inherent in state surveillance, data privacy laws, and the balance between national security and individual freedoms. Students analyze case studies such as the Snowden revelations, the EU's General Data Protection Regulation, GDPR, and the role of international bodies like the United Nations in mediating cyber conflicts. These discussions are framed through the lens of global power dynamics, emphasizing how technological sovereignty and digital infrastructure are contested assets in the 21st century. By integrating insights from political philosophy and international relations theory, students critically assess whether current governance frameworks are adequate to address emerging threats such as ransomware attacks, deepfake technologies, and the weaponization of social media. The module culminates in a student-led debate on the feasibility of a global cyber treaty, requiring them to synthesize knowledge from multiple disciplines while considering the practical challenges of international cooperation. The sentence may be useful, but the supplied evidence is insufficient to verify it confidently. This principle, rooted in the balance between vertical and horizontal velocity components, is foundational to understanding motion under gravity. Mathematically, a 45-degree angle is a critical point in geometry, often appearing in isosceles right triangles where the legs are equal, and the hypotenuse is the square root of 2 times longer. Its symmetry makes it a common feature in trigonometric calculations. In architecture, the 45-degree angle is both functional and aesthetic. It appears in the design of window grills, door frames, and even in the structural elements of bridges, where it allows for efficient load distribution. The angle's visual appeal, reminiscent of the open jaws of scissors or the greater than symbol, makes it a popular choice for decorative and structural purposes. Beyond these, the 45-degree angle's significance extends to everyday applications. For instance, when dividing a straight line into equal parts, 4 45-degree angles collectively form a 180-degree straight line, illustrating its role in spatial division. Its versatility underscores why it remains a cornerstone in fields ranging from engineering to art. The connection between geometric principles and fields like international relations becomes evident when examining how spatial reasoning influences diplomatic architecture or data visualization. For instance, the design of global communication networks, central to digital transformations, often relies on optimized angles for signal efficiency, echoing the 45-degree balance between reach and stability. Similarly, cybersecurity frameworks might employ angular configurations in network topology to distribute defense mechanisms across nodes, much like a 45-degree angle distributes force evenly in structural engineering. These intersections highlight how abstract mathematical concepts underpin real-world systems, from historical analysis to modern governance, reinforcing the idea that angles, whether 45 degrees or otherwise, serve as silent architects of both physical and conceptual landscapes. The interplay between geometric principles and global systems becomes evident when considering how spatial design influences economic and political structures. For instance, the 45-degree angle's role in optimizing solar panel efficiency aligns with the International Political Economy module's focus on resource allocation and technological advancement in regions like East Asia. Similarly, the Digital Transformations Beyond the West module might explore how digital infrastructure, such as the angles in network layouts or data visualization, shapes information dominance, echoing the historical use of geometry in architectural design to balance functionality and aesthetics. These connections underscore how abstract mathematical concepts, like the 45-degree angle, permeate both physical and virtual landscapes, shaping human interaction with the world. A 45-degree angle is a geometric angle formed when two lines intersect, creating an angle that measures exactly 45 degrees. It is significant in various fields due to its unique properties. In physics, a 45-degree angle is optimal for projectile motion, as it maximizes the horizontal distance a projectile can travel when launched under gravity. In architecture, it is used to design aesthetically pleasing structures, such as doors and window grills, which often incorporate symmetrical elements. For example, 1/4 of a 180-degree straight angle equals 45 degrees, illustrating how angles can be divided proportionally. When a straight line is split into 4 equal parts, each segment measures 45 degrees, demonstrating how geometric divisions create precise angles. The complement of a 45-degree angle is also 45 degrees, as complementary angles sum to 90 degrees. Half of a 45-degree angle is 22.5 degrees, achieved by bisecting it with an angle bisector. To measure a 45-degree angle, a protractor is used by aligning its baseline with one arm of the angle and checking if the other arm matches the 45-degree mark. The evidence sheets provided, while related to historical analysis, focus on source criticism and contextual reasoning, which are distinct from the mathematical and practical applications of 45-degree angles. They are not directly connected to the geometric concept discussed here. The modules in the International Relations, Politics and History program are designed to cultivate a nuanced understanding of global dynamics, blending theoretical frameworks with practical analysis. For instance, the Cybersecurity Governance module not only examines emerging threats, but also explores how international cooperation, or its absence, shapes the digital landscape. Students might analyze case studies such as state-sponsored cyber attacks or data privacy regulations, assessing their implications for national sovereignty and global equity. Similarly, the Digital Transformations Beyond the West module challenges students to move beyond Western-centric narratives, investigating how countries like India or South Korea navigate technological innovation while balancing cultural preservation and economic growth. These modules often culminate in interdisciplinary projects, such as simulating diplomatic negotiations or crafting policy briefs that integrate insights from political philosophy and data science. By the end of the program, students are equipped to critically engage with complex global issues, whether assessing the ethical dimensions of AI governance or evaluating the historical roots of contemporary geopolitical tensions. The emphasis on critical thinking and interdisciplinary skills ensures graduates are prepared to address real-world challenges in an increasingly interconnected world. The important geometrical concepts include perpendicular lines, meaning lines that form right angles at their point of intersection. It is commonly encountered in geometry, physics, and design due to its unique properties. For instance, when a straight line, 180 degrees, is divided into 4 equal parts, each segment measures 45 degrees. The presence of a right angle in a triangle is a defining characteristic of right triangles. In architecture, 45-degree angles are used in constructing symmetrical designs, such as window grills or door frames, to create aesthetic and functional structures. To measure or draw a 45-degree angle, one can use a protractor by aligning the baseline and vertex, or construct it by bisecting a 90-degree angle with a compass. In diagrams, the fact that an angle is a right angle is usually expressed by adding a small right angle that forms a square with the angle. These examples illustrate the practical and theoretical importance of 45-degree angles across disciplines. Euclid's work defines perpendicular lines and their relationship to right angles. By integrating insights from political science, law, and information technology, the module prepares students to address challenges such as digital sovereignty, misinformation campaigns, and the ethical implications of surveillance. The Unicode standard includes specific characters for representing right angles. The interdisciplinary nature of the program underscores the complexity of modern global challenges, where cybersecurity threats intersect with economic policies, cultural dynamics, and political strategies. The Unicode standard includes specific characters for representing right angles. Students are encouraged to analyze case studies where digital infrastructure, both physical and virtual, acts as a critical node in international power structures. The Unicode standard includes specific characters for representing right angles. These modules collectively prepare students to navigate the blurred lines between technology, politics, and history, fostering a nuanced understanding of how global systems evolve. The Unicode standard includes specific characters for representing right angles. This alignment between academic rigor and applied learning reflects the program's commitment to equipping students with the tools to engage with an interconnected, rapidly changing world. For instance, when throwing a ball, a 45-degree angle maximizes distance due to the balance between vertical and horizontal motion, a principle explored in physics. In architecture, 45-degree angles are used to design aesthetically pleasing structures, such as the diagonal lines in window grills or the symmetry of certain door frames. Two application examples in which the right angle and the Thales theorem are included. When measuring a 45-degree angle, aligning the protractor's baseline with one side of the angle and checking the other side against the 45-degree mark ensures accuracy. Additionally, understanding complementary angles is key. A 45-degree angle paired with another 45-degree angle sums to 90 degrees, demonstrating their relationship. These principles are foundational in both theoretical and practical contexts, from mathematical proofs to real-world engineering. Separately, the evidence sheets provided highlight historical analysis techniques, such as interpreting physical details in scenes to infer dates or contexts. While distinct from geometry, these methods underscore the importance of observation and reasoning in understanding both past and present phenomena. The 45-degree angle's unique properties also find application in modern technology, such as in the design of antennas for optimal signal reception or in the calibration of cameras for wide-angle lenses. In robotics, 45-degree joints are often used to balance movement and precision, allowing for smoother transitions between positions. Additionally, in the field of optics, prisms and mirrors are sometimes angled at 45 degrees to redirect light efficiently, a principle used in fiber optics and laser technology. These examples highlight how the 45-degree angle's mathematical simplicity translates into practical solutions across disciplines, reinforcing its significance beyond theoretical geometry. The interplay between spatial reasoning and historical analysis becomes evident when examining how angles, like the 45-degree shape, both physical and conceptual frameworks. In disciplines such as international relations, understanding the geometry of power dynamics or the design of diplomatic spaces, e.g., angled seating in negotiation rooms, can mirror the precision required to dissect historical artifacts or architectural remnants. Similarly, the evidence worksheet's emphasis on critical observation parallels the methodologies used in analyzing historical sources, where students must distinguish between visible data and inferred conclusions. Both processes demand a balance between empirical rigor and interpretive flexibility, whether measuring an angle's degree or contextualizing a historical event's significance. This duality underscores how seemingly disparate fields, mathematics, history, and technology, rely on structured inquiry to navigate complexity, revealing shared underpinnings in human cognition and problem-solving. The 45-degree angle, a unique geometric measurement, appears in various practical and theoretical contexts. For each sentence, decide whether it should remain unchanged or require adjustment based on the evidence. For instance, a 45-degree angle allows sunlight to reach the farthest distance, making it ideal for solar energy capture. Similarly, when throwing a ball, a 45-degree trajectory maximizes horizontal distance, a principle explored in physics. In architecture, 45-degree angles are used in design elements like doors and window grills, adding aesthetic appeal. Mathematically, a 45-degree angle is half of a 90-degree right angle, and its complement is also 45 degrees. Dividing a straight line into 4 equal parts creates 4 45-degree angles, demonstrating its role in geometric division. Beyond practical applications, the 45-degree angle also intersects with historical and academic contexts. For example, evidence-based learning tools like the I Can See, that means worksheet, encourage students to analyze visual details to infer historical contexts. These exercises require critical thinking, linking observable elements such as materials, clothing, or signage to broader historical narratives. Similarly, academic programs in international relations, such as those at Constructor University, integrate interdisciplinary studies combining political theory, history, and data science. Modules like International Political Economy explore economic shifts since the 1970s, while History of Globalization examines interconnected global developments. These programs emphasize critical analysis, preparing students to engage with complex historical and contemporary issues. Both the 45-degree angle and these academic frameworks highlight the importance of precision and reasoning. Whether in geometry, history, or international studies, understanding relationships between angles, evidence, or theories enables deeper insights. By focusing on structured observation and analytical skills, these disciplines foster a nuanced approach to problem-solving, bridging theoretical knowledge with real-world applications. The 45-degree angle is a fundamental concept in geometry, physics, and design. In physics, it is often cited as the optimal angle for projectile motion as it balances vertical and horizontal velocity to maximize distance. This principle is introduced in foundational courses, where students learn that a 45-degree trajectory allows a thrown object to travel the farthest under ideal conditions. In architecture, 45-degree angles are used to create aesthetically pleasing structures, such as the diagonal lines in modern doors and window grilles, which add both functionality and visual interest. Mathematically, a 45-degree angle is half of a right angle, making it a key component in understanding complementary angles. For instance, the complement of a 45-degree angle is also 45 degrees, as two 45-degree angles sum to 90 degrees. When dividing a straight line 180 degrees into 4 equal parts, each segment measures 45 degrees, demonstrating how this angle naturally divides a straight line into 4 equal segments. Constructing a 45-degree angle requires precision. One method involves first creating a 90-degree angle and then bisecting it using a compass, which ensures accuracy. Measuring such an angle with a protractor is straightforward. Align the protractor's baseline with one arm of the angle and check where the other arm intersects the 45-degree mark. These examples illustrate the versatility of the 45-degree angle, from theoretical mathematics to practical applications in science and design. Its significance lies in its ability to balance simplicity and functionality, making it a cornerstone of geometric and physical principles. The Cybersecurity Governance module also explores the ethical and legal challenges of balancing national security interests with individual privacy rights in an interconnected digital landscape. Students analyze case studies such as state-sponsored cyber attacks, data breaches, and the role of international law in addressing cross-border cyber threats. The module emphasizes the importance of public-private partnerships, as governments often collaborate with tech companies to mitigate risks like ransomware, disinformation campaigns, and critical infrastructure vulnerabilities. By examining frameworks such as the Budapest Convention on Cybercrime and the role of organizations like Interpol, students assess how global governance mechanisms adapt to the rapid evolution of digital threats. The course concludes with debates on whether current policies are sufficient to address emerging risks, such as artificial intelligence-driven cyber warfare or the weaponization of social media platforms. The concept of a right angle has been foundational in geometry for millennia. Defined as a 90-degree angle, it serves as a universal standard for measuring other angles. Ancient Greek mathematicians like Euclid recognized its importance, though its status as an axiom sparked debate. Proclus and Saccari attempted proofs, while Hilbert later reclassified it as a theorem. Beyond mathematics, right angles appear in practical applications, such as carpentry, where the 3-4-5 rule ensures perpendicularity. Thales' theorem further links right angles to circles, stating that any triangle inscribed in a semicircle is a right triangle. These principles extend to modern fields, including solid angles in three-dimensional geometry. In education, historical analysis tools like the evidence sheet help students develop critical thinking. This worksheet guides learners to observe physical details in historical scenes, connecting visible elements to broader contexts. By listing materials, tools, and environmental clues, students infer dates and events, emphasizing reasoning over memorization. Such exercises foster skills in source criticism and contextual interpretation, vital for understanding complex historical narratives. Academic programs in international relations also blend theory and practice. Students explore global dynamics through modules like International Political Economy, which examines economic interdependence since the 1970s, and Advanced International Relations Theory, which analyzes evolving frameworks for global governance. Courses on globalization's history and digital transformations highlight interconnected challenges, while electives in cybersecurity and data science address modern policy issues. These programs prepare students to navigate contemporary geopolitical landscapes, balancing theoretical knowledge with practical skills. Each discipline, mathematics, history, and international relations, relies on foundational principles and critical inquiry. Whether measuring angles, analyzing historical evidence, or studying global politics, the emphasis remains on rigorous reasoning and contextual understanding. These approaches ensure that knowledge is not only retained, but applied meaningfully, bridging abstract concepts to real-world relevance. The 45-degree angle, a fundamental geometric concept, appears in numerous practical and theoretical contexts. One of its most notable applications is in solar panel design. By tilting panels at a 45-degree angle, they can optimize sunlight absorption, particularly in regions where the sun's trajectory aligns with this angle. This principle also extends to physics, where projectile motion demonstrates that a 45-degree launch angle maximizes horizontal distance. Whether throwing a ball or launching a rocket, this angle balances vertical and horizontal velocity, ensuring the farthest reach. In architecture, 45-degree angles are used to create dynamic, aesthetically pleasing structures, such as the diagonal lines in modernist designs or the intricate patterns in window grilles. These angles add visual interest while maintaining structural integrity. Mathematically, a 45-degree angle is half of a right angle, making it a key component in isosceles right triangles. For instance, dividing a 180-degree straight line into 4 equal parts results in 4 45-degree angles, illustrating how such angles form a linear arrangement. When measuring, a protractor is essential to confirm the exact 45-degree mark, ensuring precision in construction or design. The complement of a 45-degree angle is also 45 degrees, as two such angles sum to 90 degrees, highlighting its symmetry. Conversely, bisecting a 45-degree angle yields a 22.5-degree angle, demonstrating how smaller increments can be derived from larger ones. Beyond practical applications, the 45-degree angle holds cultural and historical significance. In ancient geometry, it was a cornerstone of early mathematical systems, used in everything from sundial design to architectural blueprints. Its prevalence in nature, such as the angles of tree branches or the symmetry of certain crystals, underscores its universal relevance. However, while its properties are well established, interpretations of its applications can vary. For example, while a 45-degree tilt optimizes solar exposure in some regions, it may not be ideal in others due to geographical or climatic differences. Similarly, the assumption that a 45-degree launch angle always maximizes distance assumes ideal conditions, such as no air resistance, a factor often overlooked in simplified models. The study of 45-degree angles also intersects with broader scientific principles. In engineering, understanding these angles is critical for designing efficient systems, from wind turbines to aircraft wings. In education, teaching these concepts fosters spatial reasoning and problem-solving skills, preparing students for advanced mathematical and scientific challenges. While the 45-degree angle remains a foundational concept, its real-world applications continue to evolve, reflecting the dynamic interplay between theory and practice. By examining its historical roots and modern uses, we gain a deeper appreciation for its role in shaping both the physical and intellectual landscapes of our world. A 45-degree angle is a common geometric concept with practical applications in daily life. For instance, solar panels are often angled at 45 degrees to maximize sunlight absorption, depending on geographical location. Similarly, in physics, a 45-degree trajectory is optimal for projectile motion, allowing objects to travel the farthest distance. In architecture, this angle is used in designs for doors, windows, and decorative elements, adding both functionality and aesthetic appeal. Examples of 45-degree angles include dividing a straight line into 4 equal parts, resulting in 4 45-degree angles. Another example is calculating 1/4 of a 180-degree angle, which equals 45 degrees. These scenarios highlight the angle's role in geometry and real-world problem solving. The complement of a 45-degree angle is also 45 degrees, as two 45-degree angles sum to 90 degrees. Half of a 45-degree angle is 22.5 degrees, achieved by bisecting it. To construct a 45-degree angle, one can first create a 90-degree angle and then bisect it. Measuring such angles requires a protractor, aligning the tool's baseline with the angle's vertex and checking the degree markings. Historically, 45-degree angles have been significant in design and engineering. For example, ancient architects might have used such angles in structures for stability or symmetry. However, the exact methods or tools used to achieve these angles in historical contexts remain speculative, as modern precision tools were not available. The evidence sheets provided offer a framework for analyzing historical scenes by distinguishing observable details from inferred conclusions. For instance, a 45-degree angle in a historical image might suggest specific construction techniques or cultural practices, but without direct evidence, such interpretations remain tentative. This approach underscores the importance of critical analysis in historical research, where assumptions must be supported by verifiable data. In academic contexts, such as the International Relations and History program at Constructor University, students explore interdisciplinary connections between politics, history, and technology. While this field does not directly address 45-degree angles, it emphasizes the value of analytical frameworks in understanding complex systems, much like the geometric principles underpinning such angles. Ultimately, the 45-degree angle serves as a bridge between theoretical mathematics and practical applications, demonstrating how abstract concepts shape tangible outcomes. Whether in engineering, sports, or design, its significance lies in its balance between simplicity and utility, making it a versatile tool across disciplines. Important geometrical concepts include perpendicular lines, which are lines that form right angles at their point of intersection, and orthogonality, a property often associated with forming right angles, particularly in vectors. For instance, dividing a straight angle, 180 degrees, into 4 equal parts results in 4 45-degree angles, demonstrating how such angles naturally arise in spatial divisions. The meaning of right in right angle is believed to refer to the Latin adjective rectus erect, straight, upright, perpendicular. These examples underscore its practical applications in physics, architecture, and design, where angles like 45 degrees optimize functionality and aesthetics. In educational contexts, tools like the evidence sheet from historyguesser.app serve as critical thinking exercises, guiding students to analyze visual scenes by distinguishing observable details from inferred conclusions. Euclid's commentator Proclus attempted a proof of this postulate using prior postulates, though it may rely on implicit assumptions. Meanwhile, academic programs in international relations, such as those at Constructor University, integrate interdisciplinary modules that explore global politics, economics, and technology. These courses emphasize critical analysis, requiring students to evaluate complex theories and historical processes, much like the evidence-based reasoning practiced in historical inquiry. Both the 45-degree angle and these educational tools reflect the importance of structured observation and logical deduction. The solid angle subtended by an octant of a sphere is a specific case with known mathematical properties. The interdisciplinary nature of the International Relations, Politics and History (IRPH) program at Constructor University equips students to navigate complex global challenges by synthesizing theoretical frameworks with practical analysis. For instance, the History of Globalization module's exploration of interconnected systems complements the Digital Transformations Beyond the West course, enabling students to trace how historical processes intersect with contemporary technological shifts. Similarly, the Cybersecurity Governance module's focus on emerging threats aligns with the Foreign Policy, Diplomacy, and Data Science course, where students learn to apply data-driven strategies to address geopolitical risks. This integration fosters a nuanced understanding of how past and present dynamics shape international relations, preparing graduates to engage with issues like digital sovereignty, economic inequality, and transnational governance. The program's flexibility, allowing students to combine core modules with electives such as decision science for politics or empires and nation-states, ensures a tailored educational experience that balances depth with adaptability, reflecting the evolving demands of a globally interconnected world. The 45-degree angle is a fundamental concept in geometry, physics, and design, often celebrated for its unique properties and applications. The solid angle subtended by an octant of a sphere is approximately pi over 2 SR. Examples of 45-degree angles. 1. Example 1. If you divide a straight line 180 degrees into 4 equal parts, each segment measures 45 degrees. This is why a straight line can be split into 4 45-degree angles. 2. Example 2. In architecture, a 45-degree angle is used to create symmetrical designs, such as the diagonal lines in window grills or the slope of a roof. For instance, a roof with a 45-degree pitch ensures equal weight distribution and aesthetic balance. Our key applications, physics, throwing a ball at a 45-degree angle maximizes its horizontal distance due to the optimal balance between vertical and horizontal velocity components. In robotics or machinery. In robotics or machinery, 45-degree angles are used for efficient gear alignment or structural stability. Art and design. Artists use 45-degree angles to create dynamic perspectives, such as in perspective drawing or modernist architecture. Frequently asked questions. Q. What does a 45-degree angle look like? A. It resembles the open jaw of scissors, or the angle formed by splitting a right angle, 90 degrees, into 2 equal parts. Q. What is the complement of a 45-degree angle? A. The complement is 45 degrees, since 90 degrees minus 45 degrees equals 45 degrees. Minus Q. How many 45-degree angles make a full turn? 360 degrees. A. Create 8, since 45 degrees times 8 equals 360 degrees. Chris Q. How to measure a 45-degree angle? A. Use a protractor by aligning its baseline with one arm of the angle and checking where the other arm intersects the 45-degree mark. Academic context. While the 45-degree angle is a mathematical concept, its applications span disciplines. For instance, in international relations, understanding angles and spatial relationships might metaphorically relate to analyzing geopolitical boundaries or strategic positioning. Similarly, historical analysis, like the evidence sheet mentioned, requires critical observation, much like identifying angles in architectural designs. However, these connections are indirect and more conceptual than technical. In summary, the 45-degree angle remains a cornerstone of geometry, offering practical solutions in science, engineering, and art, while its theoretical underpinnings continue to inspire interdisciplinary exploration. The academic program in International Relations, Politics, and History at Constructor University offers students a structured pathway to deepen their understanding of global dynamics. In their second year, students engage with 45 credit points, CP, of discipline-specific core modules, building on foundational knowledge from introductory courses. Mandatory core modules include International Political Economy, which examines the interplay between economics and international relations since the 1970s, with a focus on China's rise. Advanced International Relations Theory explores theoretical frameworks shaping world politics over the past 6 decades, while the history of globalization traces the evolution of interconnected systems from the modern era. Elective modules allow students to specialize further, such as empires and nation-states, which analyzes historical forces shaping modern societies, or cybersecurity governance, which assesses global efforts to address digital threats. These modules equip students with critical analysis and practical skills, preparing them for careers in diplomacy, policy, or academia. Beyond academics, students engage with historical inquiry through tools like the Evidence Sheet worksheet. This activity challenges learners to observe and interpret visual scenes, listing tangible details, such as materials, clothing, or signage before inferring contextual information. The exercise emphasizes reasoning over guesswork, requiring students to justify their conclusions with historical context. For example, identifying a specific architectural style or technological artifact can narrow down a scene's time frame. The process encourages reflection on the reliability of evidence, asking students to consider what details might be missing or misinterpreted. By balancing observation with critical thinking, the worksheet fosters historical literacy, helping students distinguish between plausible inferences and speculative assumptions. Both academic and historical inquiry rely on structured frameworks to navigate complexity. The university's modules blend theoretical rigor with real-world applications, while the evidence sheet underscores the importance of methodical analysis in interpreting the past. Together, these approaches highlight how knowledge is constructed through disciplined observation, critical evaluation, and contextual awareness. Whether analyzing global political systems or reconstructing historical events, the emphasis remains on grounding conclusions in verifiable evidence, ensuring that interpretations are both informed and nuanced. The 45-degree angle is a fundamental concept in geometry, physics, and design. In physics, it is optimal for projectile motion, as it balances vertical and horizontal velocity to maximize distance. In architecture, it is used in door and window designs for aesthetic and structural purposes. Mathematically, a 45-degree angle is half of a right angle, 90 degrees, and is often found in isosceles right triangles, where the two non-right angles are each 45 degrees. For example, dividing a 180-degree straight angle into 4 equal parts results in 4 5-degree angles. Its complement is also 45 degrees, as 90 degrees minus 45 degrees equals 45 degrees, and half of a 45-degree angle is 22.5 degrees. To measure it, a protractor aligns with the angle's vertex and arms. While unrelated to the topic, the provided academic modules and evidence worksheets highlight the importance of critical analysis in historical and scientific contexts, emphasizing the need to verify claims with reliable sources. The History of Globalization module's exploration of interconnectedness could also intersect with the practical applications of 45-degree angles, such as in the spread of architectural techniques or technological standards across cultures. For instance, the adoption of 45-degree angles in modern design, whether in solar panel installations or urban infrastructure, reflects a global exchange of engineering principles. Similarly, the Digital Transformations Beyond the West module might examine how digital tools enable the precise calculation of such angles, bridging traditional craftsmanship with contemporary data-driven methodologies. These connections highlight how academic disciplines, even those seemingly abstract, often underpin real-world innovations and cultural exchanges. The study of angles, such as the 45-degree angle, intersects with disciplines like history and international relations through the analysis of spatial design and symbolic structures. For instance, ancient architectural marvels, such as the stepped pyramids of Mesoamerica or the geometric layouts of medieval cities, often incorporated precise angles to reflect cultural values or astronomical alignments. In the History of Globalization module, students might explore how such angular designs facilitated trade routes or symbolized power dynamics between empires. Similarly, in the Digital Transformations Beyond the West module, the interplay of angles in modern urban planning, such as the 45-degree inclines in sustainable infrastructure, could be examined as a continuation of historical spatial strategies. These connections highlight how mathematical principles underpin both tangible and abstract aspects of human civilization, bridging the gap between technical precision and cultural interpretation. The 45-degree angle is a fundamental concept in geometry, often encountered in practical applications and theoretical contexts. It is an acute angle formed when a line is bisected from a right angle, 90 degrees, resulting in two equal angles of 45 degrees each. This angle is significant in various fields. Minus physics. A 45-degree angle is optimal for projectile motion, as it maximizes the horizontal distance a projectile can travel when launched under gravity. Architecture. Designers use 45-degree angles in structures like window grills, door frames, and decorative elements for symmetry and aesthetic balance. Mathematics. It is a key component of isosceles right triangles, where the two legs are equal and the hypotenuse is the square root of 2 times longer. Examples. 1. Dividing a 180-degree straight angle into 4 equal parts results in 4 45-degree angles. 2. A 45-degree angle's complement, the angle needed to sum to 90 degrees, is also 45 degrees. Half of a 45-degree angle is 22.5 degrees, achieved by bisecting it. Measurement. A protractor is used to measure a 45-degree angle by aligning its baseline with one arm of the angle and checking the 45-degree mark on the protractor's scale. The provided evidence sheets and academic modules from Constructor University, while unrelated to the mathematical concept, offer context for integrating interdisciplinary learning. For instance, historical analysis via evidence sheets might explore how ancient builders used geometric principles, while the IRPH program's modules could discuss the role of geometry in globalized societies. However, these connections are contextual and not directly tied to the mathematical properties of a 45-degree angle. The program's interdisciplinary approach ensures students engage with complex global challenges, blending theoretical frameworks with practical analysis. For instance, the Digital Transformations Beyond the West module encourages students to critically assess how non-Western societies navigate technological shifts, contrasting with Western-centric narratives. This fosters a nuanced understanding of power dynamics in the digital age. Meanwhile, the Decision Science for Politics module equips students with tools to analyze political choices through behavioral economics and game theory, preparing them for roles in policymaking or corporate strategy. Such modules reflect the program's commitment to cultivating adaptable thinkers capable of addressing contemporary issues like climate governance or digital ethics. By integrating diverse perspectives, the curriculum aims to bridge academic rigor with real-world applicability, ensuring graduates are well-versed in both historical contexts and modern geopolitical landscapes. For each sentence, assess whether it should remain unchanged. This angle is also significant in physics, where it is noted that a projectile launched at a 45-degree angle achieves maximum range due to the balance between vertical and horizontal components of motion. In architecture, 45-degree angles are used to create aesthetically pleasing designs, such as the diagonal lines in window grills or the symmetry in door structures. To measure a 45-degree angle, a protractor is typically used, aligning the baseline with one arm of the angle and checking the other arm against the 45-degree mark. Constructing such an angle often involves first creating a 90-degree angle and then bisecting it. The complement of a 45-degree angle is also 45 degrees, as their sum equals 90 degrees. Additionally, 8 45-degree angles are required to form a full rotation of 360 degrees. These examples illustrate the versatility and importance of the 45-degree angle across various disciplines. The program's interdisciplinary approach ensures students develop a nuanced understanding of global dynamics, blending theoretical analysis with practical applications. For instance, the Digital Transformations Beyond the West module equips students to critically assess how non-Western societies navigate technological shifts, while the Decision Science for Politics module bridges behavioral economics and policymaking. This structure prepares graduates for careers in diplomacy, international organizations, media, or academia, emphasizing adaptability in an interconnected world. Students are encouraged to engage with contemporary issues such as climate governance or digital sovereignty through capstone projects that integrate insights from multiple disciplines. The program's flexibility also allows for interdisciplinary minors, fostering expertise in areas like environmental policy or global health, thereby broadening career pathways while maintaining academic rigor. The program's interdisciplinary approach ensures students engage with contemporary issues such as digital sovereignty, climate diplomacy, and transnational security, fostering a nuanced understanding of how historical contexts shape modern policy debates. By integrating theoretical frameworks with practical case studies, graduates are equipped to analyze complex global challenges, from the ethical implications of AI and statecraft to the geopolitical ramifications of resource scarcity. This balance between critical analysis and applied skills prepares students for careers in think tanks, governmental agencies, or international organizations, where the ability to navigate intersecting political, economic, and cultural dynamics is essential. The important geometrical concepts are perpendicular lines, meaning lines that form right angles at their point of intersection. In physics, it is often noted that a 45-degree angle is optimal for projectile motion, as it balances the vertical and horizontal components of velocity to maximize distance. This principle is foundational in understanding mechanics and is typically introduced in physics courses. In architecture, 45-degree angles are used to create aesthetically pleasing designs, such as in the construction of doors and window grills, where they contribute to both structural integrity and visual appeal. For instance, dividing a 180-degree angle into 4 equal parts results in 4 45-degree angles, demonstrating how such angles can be derived from more complex measurements. Similarly, a straight line divided into halves and then into quarters produces multiple 45-degree angles, illustrating their role in geometric divisions. These examples highlight the practical applications of 45-degree angles, reinforcing their significance in both theoretical and applied fields. The precision and symmetry associated with these angles make them a recurring theme in mathematics and design, underscoring their universal relevance. The modules in the International Relations and Politics program at Constructor University are designed to equip students with the analytical tools to navigate complex global challenges. For instance, the Cybersecurity Governance module, which examines threats to digital infrastructure and global governance responses, might intersect with technical disciplines where geometric principles, like angles, play a role in designing secure systems or optimizing network layouts. Similarly, the Digital Transformations Beyond the West module, which explores how state and corporate actors influence societies through information control, could involve spatial data analysis or infrastructure planning, areas where angles and measurements are critical. These interdisciplinary connections highlight how the program prepares students to address real-world issues by integrating historical, political, and technological perspectives. Such skills are increasingly vital in a world where global challenges demand both theoretical insight and practical expertise across diverse fields. The Cybersecurity Governance module considers which threats to cybersecurity have emerged, analyzes the global governance efforts that have been made to tackle these threats, and reflects on how these efforts could be organized differently. Students examine the rise of ransomware attacks, state-sponsored cyber espionage, and the vulnerabilities of critical infrastructure, while assessing frameworks like the Budapest Convention on Cybercrime and the role of the United Nations in establishing norms for digital security. The module also explores tensions between national sovereignty and cross-border cooperation, highlighting how fragmented regulatory environments complicate responses to transnational cyber threats. By engaging with case studies such as the SolarWinds breach and the Colonial Pipeline ransomware incident, students critically evaluate the balance between proactive defense, international law, and the ethical implications of surveillance technologies in the digital age. Important geometrical concepts include perpendicular lines and orthogonality. For instance, solar panels are often angled at 45 degrees to optimize sunlight absorption based on geographical location. Similarly, in physics, a 45-degree trajectory maximizes the distance a projectile, like a thrown ball, can travel. In architecture, 45-degree angles are used to design aesthetically pleasing structures, such as decorative window grilles and doors. These examples highlight the angle's utility in both scientific and artistic contexts. When analyzing historical sources, students engage in critical thinking by evaluating physical evidence. For example, an evidence sheet might prompt learners to observe details like materials, tools, or signage in a historical scene. By connecting these observations to broader historical contexts, students infer dates and events. This method emphasizes reasoning over memorization, fostering deeper understanding. In academic programs such as international relations and history, students explore complex topics through structured modules. For instance, a module on international political economy examines economic shifts since the 1970s, while another on globalization traces historical interconnectedness. These courses blend theoretical analysis with practical skills, preparing students for advanced study or professional careers. The interplay between geometry and history underscores the value of interdisciplinary thinking. A 45-degree angle's mathematical precision mirrors the analytical rigor required in historical research. Both fields demand careful observation, logical deduction, and an awareness of context. Whether measuring angles or interpreting artifacts, the goal is to uncover patterns and meanings that transcend surface-level details. By integrating mathematical principles with historical inquiry, students develop versatile skills. The 45-degree angle, as a simple geometric concept, becomes a metaphor for the balance between structure and interpretation. This duality reflects the broader challenge of understanding both the tangible and intangible aspects of human experience. The concept of a right angle, defined as an angle of 90 degrees or pi over 2 radians, has been foundational in geometry since antiquity. The International Political Economy module examines the relationship between economics and international relations since the 1970s, with particular attention to developments in China and East Asia. The Pythagorean triple 3, 4, 5 remains a practical tool for verifying right angles, while Thales' theorem highlights its geometric significance in circles. These principles are supported by classical texts like Euclid's Elements, though their formalization required later developments in axiomatic systems. In educational contexts, tools like the evidence sheet, I can see that means encourage critical analysis by linking observable details to historical inferences, fostering reasoning over rote memorization. Meanwhile, academic programs such as Constructor University's International Relations major integrate interdisciplinary modules blending political theory, globalization, and data science to explore contemporary global challenges. These materials, while informative, reflect broader educational frameworks rather than direct historical claims. When evaluating sources, it is essential to distinguish between foundational mathematical knowledge, which is well supported, and contextual educational resources, which provide supplementary insight but require cautious interpretation. All claims must align with the evidence provided, avoiding speculation or invention. The concept of the right angle extends beyond classical geometry into modern applications, such as coordinate systems and vector analysis. In Cartesian coordinates, the x-axis and y-axis intersect at a right angle, forming the foundation for plotting points and analyzing spatial relationships. This perpendicularity is critical in fields like physics, where vectors are often decomposed into orthogonal components to simplify calculations. For instance, forces acting at right angles can be treated independently, reducing complex problems into manageable parts. In computer graphics and engineering, right angles underpin the design of structures and algorithms. The stability of buildings, bridges, and even digital images relies on right angles to ensure alignment and balance. Additionally, in trigonometry, right triangles are central to defining sine, cosine, and tangent functions, which are indispensable in modeling periodic phenomena like sound waves or planetary motion. The historical significance of right angles also resonates in cultural contexts. Ancient civilizations, such as the Egyptians and Greeks, used right angles in construction and art, reflecting their universal utility. Even in contemporary contexts, the right angle remains a cornerstone of mathematical rigor, bridging theoretical abstraction with practical problem solving. Its enduring relevance underscores the interplay between geometric principles and human innovation. In the first example, dividing a 180-degree angle into 4 equal parts results in 4 45-degree angles, demonstrating the relationship between fractions and angles. The second example shows how a straight line can be divided into 4 45-degree angles through sequential halving, highlighting the geometric properties of angles. These examples underscore the precision and utility of 45-degree angles in both theoretical and applied contexts. The evidence sheets, meanwhile, focus on teaching students to critically analyze historical scenes by distinguishing between observable details and inferred conclusions. By listing what is physically visible, such as materials, tools, or clothing, and then linking those observations to broader historical contexts, students learn to evaluate the reliability of their interpretations. This method emphasizes reasoning over memorization, a skill that could complement interdisciplinary studies such as those in the International Relations Program, where critical analysis of historical and contemporary events is central. The university program's modules, which explore topics like international political economy and the history of globalization, might benefit from such evidence-based approaches. For instance, analyzing historical artifacts or documents through a similar framework could enhance students' ability to contextualize theoretical concepts. However, the connection remains indirect, as the evidence sheets and the program's curriculum serve distinct educational goals. In both cases, the emphasis on structured observation and logical deduction reflects a broader educational philosophy, grounding knowledge in verifiable details while fostering analytical thinking. Whether in mathematics, history, or international studies, this approach ensures that conclusions are built on a foundation of evidence rather than speculation. The interdisciplinary nature of the International Relations and History program at Constructor University mirrors the multifaceted applications of geometric principles like the 45-degree angle. For instance, in the Digital Transformations Beyond the West module, students analyze how technological innovations, such as solar panel designs optimized with 45-degree angles for maximum sunlight absorption, reflect broader geopolitical strategies in sustainable development. Similarly, the History of Globalization module might explore how architectural elements, like 45-degree angles in modernist design, symbolize cultural intersections during periods of rapid urbanization. These connections highlight how abstract concepts, whether mathematical or historical, shape tangible realities. Meanwhile, the evidence worksheet's emphasis on critical observation parallels the program's focus on source analysis, where students must discern between visible details and inferred conclusions, much like identifying a 45-degree angle in a historical artifact versus its functional purpose. Both approaches require rigorous reasoning, bridging the gap between empirical observation and theoretical interpretation. The 45-degree angle is a fundamental concept in geometry, often encountered in various real-world applications and mathematical contexts. The rule of 3-4-5 is a method to confirm if an angle is a true right angle. Here's a breakdown of its significance and examples. 1. 2 application examples involving the right angle and Thales' theorem. This is due to the balance between vertical and horizontal velocity components, a principle explored in projectile motion. Unicode 5.2 includes mathematical operators and miscellaneous mathematical symbols. B. Architecture and design. Architects use 45-degree angles to create symmetrical and aesthetically pleasing structures, such as diagonal window grills or modern door designs. Heath's work discusses the properties of right angles. 3. Mathematical applications. Angle bisectors. A 45-degree angle can be formed by bisecting a 90-degree angle. For instance, dividing a straight line 180 degrees into 4 equal parts results in 4 45-degree angles. Complementary angles. The complement of a 45-degree angle is also 45 degrees, as 90 degrees minus 45 degrees equals 45 degrees. Minus half of a 45-degree angle Bisecting a 45-degree angle yields a 22.5-degree angle, often constructed using a compass and straightedge. 4. Measurement techniques. A protractor is used to measure a 45-degree angle by aligning its baseline with one arm of the angle and checking where the other arm intersects the 45-degree mark. 5. X construction with compass. To draw a 45-degree angle, first construct a 90-degree angle using a compass, then bisect it with another arc to achieve the desired angle. These examples highlight the versatility of 45-degree angles in both theoretical and practical contexts. While the provided evidence sheets relate to history and academic programs, they do not directly connect to the mathematical properties of 45-degree angles. The focus remains on the geometric and applied significance of this angle. Another practical application of 45-degree angles lies in the field of computer graphics and animation, where they are essential for creating smooth transitions and realistic motion. For instance, when designing 3D models or rendering visual effects, artists often use 45-degree angles to simulate natural lighting and shadows, enhancing the depth and realism of digital scenes. In engineering, 45-degree angles are frequently employed in the construction of ramps and inclines, as they provide an optimal balance between steepness and ease of traversal. This is particularly evident in wheelchair accessibility design, where a 45-degree slope ensures safety while maintaining functionality. Additionally, in the realm of sports, athletes like gymnasts and skiers utilize 45-degree angles in their routines to maximize momentum and control, demonstrating how this geometric principle transcends theoretical contexts into everyday life. The 45-degree angle is a fundamental concept in geometry, often encountered in physics, architecture, and everyday applications. For instance, when throwing a ball, a 45-degree angle maximizes distance due to projectile motion principles. In architecture, 45-degree angles are used in designing doors and window grills for aesthetic and structural balance. Mathematically, a 45-degree angle is half of a right angle, 90 degrees, and it can be constructed by bisecting a 90-degree angle. Examples include dividing a straight line, 180 degrees, into 4 equal parts, resulting in 4 45-degree angles. The complement of a 45-degree angle is also 45 degrees, as angles summing to 90 degrees are complementary. Measuring such angles requires a protractor, aligning the tool's baseline with one arm of the angle and checking the 45-degree mark. The evidence sheets provided are educational tools for history classes, focusing on source criticism. Students analyze visual scenes by listing observable details, e.g., materials, clothing, signage, and infer contextual information such as the historical period. These sheets encourage critical thinking by linking physical observations to broader historical narratives. For example, a scene with a specific type of transportation or architecture might narrow down the possible time period. The exercises emphasize reasoning over memorization, with assessments based on the logic of inferences rather than factual recall. The International Relations program at Constructor University highlights interdisciplinary studies, combining political theory, history, and data science. Modules like International Political Economy and History of Globalization explore economic interdependence and historical trends, while courses on cybersecurity and digital transformations address modern challenges. These programs aim to equip students with analytical skills to understand complex global issues, blending theoretical knowledge with practical applications. The provided sources and rules caution against assuming all claims are accurate, emphasizing the importance of evidence-based reasoning. When integrating such materials, clarity and adherence to the specified guidelines are essential to avoid misinterpretation. The 45-degree angle's prevalence in both natural and human-made systems underscores its efficiency in balancing form and function. In historical contexts, such angles often appear in architectural designs, like the sloped roofs of traditional Japanese tea houses or the geometric patterns in Islamic art, where symmetry and structural stability are paramount. These angles not only serve practical purposes, but also reflect cultural aesthetics, making them a subject of study in fields like art history and archaeology. Similarly, in modern technology, 45-degree angles are critical in the design of antennas for optimal signal reception or in the engineering of wind turbines where aerodynamic efficiency is key. The interplay between geometry and utility continues to shape innovation, bridging ancient craftsmanship with contemporary science. The 45-degree angle holds a unique place in both practical and theoretical contexts. So the focus is on reasoning rather than the score. When you throw a ball, aiming it at 45 degrees balances the vertical and horizontal components of motion, allowing gravity to act on the object while maintaining forward momentum. This concept is foundational in kinematics. In architecture, 45-degree angles are used to create dynamic, symmetrical designs. Think of the diagonal lines in modern doors or window grills. These angles add visual interest without compromising structural integrity. They also play a role in ensuring stability in frameworks, distributing weight evenly. Mathematically, a 45-degree angle is half of a right angle, making it a key component in geometry. For instance, dividing a 180-degree straight line into 4 equal parts results in 4 45-degree angles. This is why a straight line can be split into 4 45-degree segments, each contributing to the total 180 degrees. When measuring a 45-degree angle, a protractor is the standard tool. Align the baseline of the protractor with one arm of the angle and the vertex with the center mark. The other arm should intersect the 45-degree marking. If it does, the angle is confirmed. The complement of a 45-degree angle is also 45 degrees, as complementary angles sum to 90 degrees. Halving a 45-degree angle yields 22.5 degrees, which can be constructed by bisecting the original angle with a compass. To draw a 45-degree angle, one first constructs a 90-degree angle and then bisects it using geometric techniques. These properties make the 45-degree angle a versatile and essential concept, bridging mathematics, physics, and design. Its simplicity and precision allow it to be applied across disciplines, from calculating trajectories to crafting elegant architectural details. The study of angles, such as the 45-degree angle, also intersects with historical analysis, where students use tools like the evidence sheet to interpret visual data. For instance, when examining architectural remnants from ancient civilizations, the presence of 45-degree angles in structures like doorways or window frames can hint at the mathematical knowledge of the era. Similarly, in the context of international relations, understanding spatial relationships, whether through maps or geopolitical diagrams, requires an awareness of angles and their implications for territorial boundaries or strategic positioning. These connections underscore how mathematical principles, even in their simplest forms, underpin both practical applications and scholarly inquiry across disciplines. A 45-degree angle is a fundamental concept in geometry, often encountered in both theoretical and practical contexts. Its significance extends beyond mathematics, influencing fields like physics, architecture, and engineering. For instance, in physics, a 45-degree angle is optimal for projectile motion, as it maximizes the horizontal distance a projectile can travel when launched under ideal conditions. In architecture, 45-degree angles are used to create aesthetically pleasing designs, such as the diagonal lines in window grills or the symmetry of certain door structures. When dividing angles, a 45-degree angle emerges naturally. For example, 1/4 of a 180-degree straight angle is exactly 45 degrees, and splitting a 90-degree right angle into 2 equal parts also yields 2 45-degree angles. This property is useful in construction and design, where precise measurements are critical. Additionally, A full rotation of 360 degrees contains 8 45-degree angles, highlighting its role in circular measurements and rotational symmetry. To measure or construct a 45-degree angle, tools like a protractor or compass are essential. A 45-degree angle can be drawn by bisecting a 90-degree angle, a technique that relies on geometric principles. Its complement, the angle needed to sum to 90 degrees, is also 45 degrees, making it a key component in trigonometric calculations. Half of a 45-degree angle is 22.5 degrees, which can be achieved by further bisecting the 45-degree angle. These examples and properties demonstrate the versatility of the 45-degree angle, bridging abstract mathematical theory with real-world applications. Its simplicity and symmetry make it a cornerstone in both academic study and practical problem-solving. The interplay between historical analysis and academic disciplines like international relations, politics, and history reveals how critical thinking frameworks, such as those honed through evidence sheets, inform interdisciplinary studies. For instance, the meticulous observation and reasoning required to deduce a scene's timeline mirror the analytical rigor needed to dissect geopolitical theories or digital transformations. In the History of Globalization module, students grapple with interconnected systems, much like historians reconstructing past events from fragmented clues. Similarly, the Digital Transformations Beyond the West module's focus on information networks parallels the evidence sheet's emphasis on contextualizing visible details within broader historical or cultural frameworks. These skills, questioning assumptions, cross-referencing sources, and synthesizing disparate data, form the bedrock of both historical inquiry and contemporary policy analysis, bridging the gap between past and present in ways that shape future academic and professional trajectories.